Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, selamat siang, salam sejahtera. Thank you for coming to this actually very special time in our seminar Reboan. So we do this every week. We invite different speakers internationally, sometimes online, sometimes offline when they are abroad, basically. So this is the platform where we hopefully introduce new fields of research or give insights about what we are doing and what the researchers are doing and so on and so forth. So this is really a special time for us because with us now is Professor Andrea Baldi, although he doesn't like to be called professor, so just call him Andrea. It's very polite, trust me, just call him Andrea. No other surnames, no professors, nothing. Andrea is an expert in the fields of nanoplasmonics. We will learn what it is. So I had the chance to know Andrea back since 2014. So we met at Manchester during one of the conferences. And then I'm lucky enough again to work with Andrea since 2020 for almost 4 years. So I work as a postdoctorate. And there I know that Andrea is really a nerd in a positive way. He loves science. He loves talking about science, and he definitely wants you to enjoy science as much as he does. So this is a really honor for us. We will learn not only what Andrea is doing, but hopefully it will give us new insight and hopefully can inspire the research here in UI or maybe in other department. So without further ado, I think I will let Andrea introduce himself and please enjoy the talk. Will be a treat for us because Andrea is a really good speaker. So the burden is in your shoulder.
I can only disappoint after this introduction, so I'm sure I will disappoint. Thank you very much, Ferry, for the very kind introduction and also for the invitation. Arrived on Saturday, and I hope won't be the last time. So I'm actually a chemist by education, and I know that I'm talking in a physics department. Not only am I a chemist talking in a physics department, I put a title, chemistry. So I'm going to talk about plasmonic chemistry. And so I realize that can be confusing, but I can assure you that there is going to be very little chemistry and actually quite a lot of physics. So hopefully you'll bear with me until we get to the ends of this presentation. So what I'm going to be talking about is about plasmonics and plasmonic chemistry. And I like to give talks that are also a little bit didactic. And so I'm going to introduce the field of plasmonics and tell you what we mean by that. And essentially that is shining light on nanoscale metal objects. And by doing that, we can actually activate processes at the surface of these objects like chemical reactions. So that's essentially the title, the main theme of the talk. So this is actually the Vrije Universiteit. That's where I work. Let me just do this for a second. The Vrije Universiteit on a sunny day in Amsterdam, which is not very often, unfortunately. The office where we are sitting is down here, and this is the main building. Here is where our students are learning, and now we're getting a new building for the physics department on this side. So everyone is really welcome to come visit. I know that there is also fellowships for PhD students or master internships or postdocs that want to do one of their experiences abroad. My email is on the slide for a reason. Please reach out to me if that's at all your interest, or if you know someone that might be interested in that. I should also acknowledge the people that actually did the research that I'm going to be talking about. This is only a short list of the people that are in the group, but they are the main people that did the work that I'm going to be discussing in terms of research papers that I'll show you. And also the funding institutions, of course. Now, this is the group, actually. This is our photoconversion materials sections. We work on materials and we synthesize materials and then characterize their optical properties. That's why we call ourselves photoconversion materials. This was last summer, and I'm showing this picture to show you how nice and diverse our group is, but also here where you can see Dr. Ferry waving from the back. So it's true, he was in the group. Now, what do we do? In the group, we have essentially, in my group, we synthesize nanomaterials. So that's my chemistry background. We like to go in the chemistry lab and actually make nanomaterials from scratch, from the bottom up, both with colloidal chemical synthesis, but also with nanolithography techniques. And then essentially we shine light on them. And the reason why we do that is because we want to activate chemical reactions, and that's part of the story that I'm going to tell you today, plasmon-driven chemical reactions. We also want to detect processes. For example, we can use these nanomaterials to detect gases or to detect temperature increases at the nanoscale. And we have a few contributions on there. We can also arrange them in regular arrays. And in this way, the nanomaterials are not just interacting with light, but actually the light that is scattered by one nanomaterial is interacting with the light scattered by the next one. And so we can exploit emergent properties out of this collective behavior. So, but today I don't have the time to introduce the field of plasmonics and plasmonic chemistry and then go through all of this. I would bore you to death. So this is the part that I'm going to be discussing about. I'm going to tell you the story of how we started working on how we can control chemical reactions using light and plasmonic resonances, and essentially the kind of learned lessons that we got through the way. And the general motivation is this, like, why do we want to do it? Well, there was this paper that came out a few years ago called Applying Plasmonics to a Sustainable Future. And in the paper, they recognize that chemistry is fundamental for powering our society. Think of, the amount of energy that we spend to make ammonia, for example, which is fertilizing our grounds. And what they write is that plasmonics offers the ultimate spatial and temporal control over light and photochemistry. Essentially, by coupling light into nanomaterials, we can control charge carriers, heat, electromagnetic fields, both in space at the nanoscale and also in time if we use like ultra-fast light pulses. I'm not going to talk about ultra-fast light pulses. That's a whole different kind of words that we can get into. So that's the title of my talk. What am I going to be talking about? First of all, what do we mean by plasmonics? Plasmonics, for the people of you that are familiar with the field of photonics or nanophotonics, that can mean many different things. In our case, we really confine ourselves into plasmon resonances in metal nanoparticles. This is what we call localized plasmon resonances. Why and how do we want to use plasmonics for chemistry? What are the physical mechanisms that underpin the interest of using these nanomaterials for chemical applications? And finally, we'll tell you the story of what kind of learned lessons we had. How did we start our journey and where did we end up? Okay, so what do we mean by plasmonic? Well, it's very simple. So if you have a metal nanoparticle, a nano object made of metal, and you shine electromagnetic plane wave on it, this is essentially energy is dissipated. And the reason why these metal nanoparticles can do it is because they have free electrons in the metal. And so these electrons can resonate at frequencies that are commensurate with the frequency of light, particularly visible or infrared light. And so the interaction can be very strong. Now, if you want to really solve this problem from a physical, ground, let's say you have to solve the problem of a plane wave hitting on a spherical object. And that's kind of trying to fit a round peg in a square hole, right? It's a little bit complicated mathematically. And if you read the book that actually describes this physical problem, they write, the reader who has painstakingly followed the derivation acquired virtue through suffering. So I don't have the time to impose on you any suffering or give you any virtue, but you will see that we can find like an approximation that works good enough in certain conditions. And that should lead you to understand what is a plasmon resonance in the end. Okay, how do we conceptualize plasmon resonances? We use a concept called cross-section. This is very common in physics, of course. And so since these particles can either scatter or absorb light, we call them scattering cross-section or an absorption cross-section. And the extinction would be the sum of the two. So essentially, if a particle can scatter or absorb, and anything that is not scattered or absorbed will be will be transmitted, or the sum of scattering and absorption is extinction. Now you can see that the scattering cross-section, first of all, they have a size of an area. So we express them as square meter. So in a way, the extinction cross-section, you can think of it as the area of the shadow that one of these particles would cast on a screen behind it. So for a microscopic object, let's say a tennis ball or a soccer ball, if you shine light onto it and there is a screen behind it, the shadow will have an area that is roughly pi r squared. Right? Now, nanoparticles don't behave like microscopic objects. Like molecules, for example, can have cross-sections that are hundreds or thousands of times smaller than their physical areas. Nanoparticles actually can have cross-sections that are larger than their physical areas, but that's one characteristic. And both the scattering and absorption cross-section, they depend on a quantity that is called alpha, which is called the polarizability. And the polarizability of an object So this is a property of an object that depends on the permittivity of its materials. And we know that the permittivity from basic physics is a measure of how easy it is to polarize a material under a given electric field. So if you have an electromagnetic wave or inside a material propagating, the amount of polarization, of charge separation you get into the material is quantified in terms of the polarization vector, and the polarization vector will be proportional to the permittivity of that material. For a given electric field, E, the larger the permittivity, the larger the polarization. Now, this is a property of a material, so it's independent on the shape or in the size. But an object, like, for example, a spherical particle of a certain metal in a medium, let's say in air or in vacuum, then the polarizability of that object will depend on the permittivity of that metal and of the surrounding environment. Okay, so how do we write down the polarizability? Because from the polarizability, we can get the scattering and the absorption cross-section, and we can understand how these nanoparticles interact with light. Well, there is an easy approximation that only works, though, if you have particles that are much, much smaller than the wavelength of the electromagnetic wave that you're shining on them. So this would be, for example, the case if you have a metal nanoparticle that is only a few nanometers across, or maybe a few tenths of nanometers, and you shine visible light on it, right? Visible light, we have it in between 400 and 700 nanometers. So a nanoparticle would be much smaller than that wavelength. So this approximation actually holds in this case. Now, if you are in this approximation, actually, what happens is that you can treat your nanoparticle not as a three-dimensional object, but as a point dipole. In fact, the solution to the full equation, full treatment, the virtue and suffering, reduces into a point dipole that scatters light and absorbs light. And so the polarizability is actually the polarizability of a dipole. We can think of a particle essentially as a point dipole. Like the electromagnetic field is changing so slowly with respect to the size of the particle that the particle dimensions don't count anymore. And so now the polarizability is given only by the volume, 3 times the volume. And then there is this ratio, is epsilon minus epsilon m over epsilon plus 2 epsilon m, where epsilon is the permittivity of the particle, so the metal that in this case that is composing the particle, and epsilon m would be the permittivity of the surrounding medium. Let's say in vacuum that would be 1, right? So if we have a nanoparticle in vacuum or in air, then this would be 3 times the volume, epsilon 1 is 1, epsilon over epsilon plus 2. And the interesting thing is that now we have a resonance condition, if you look carefully, because at the so-called Froelich condition, when the permittivity of the metal is minus 2 times the permittivity of the surrounding medium, then the denominator becomes vanishingly small, the polarizability becomes extremely large, and therefore the scattering and the absorption cross-section also become very large. So at that precise condition, we expect the nanoparticle to scatter very much and absorb very much. And so we have what we call a plasmon resonance. So let me give you an example. This is a typical plasmonic metal that we use is silver. And the reason why we use silver is because we like to shine visible light. It's easy to produce and to detect. And silver in the visible range is a very good conductor. So essentially the losses in the materials are negligible. And so the permittivity, which is typically defined by a real component and an imaginary component, the imaginary component of silver in the visible, in fact, here I'm plotting between 300 and 500 nanometers. So this would be UV and maybe some blue part of the spectrum. The imaginary component is 0. So we can neglect all the losses in silver. And we can think that the permittivity is essentially given by the real component of the permittivity. So now a question to you, like given the Froelich condition that we have seen before, I think this died. Given this Froelich condition that says that we have a resonance where epsilon is minus 2 times epsilon m, where do you expect a plasmon resonance if you have a silver nanoparticle in vacuum? At which wavelength? And I recognize that from the back is going to be very hard. Should be possible. And I'll drink some water. Where do we have the Froelich condition? sorry, 350, right? So we want the permittivity to be -2 times the permittivity of the surrounding medium. The surrounding medium is vacuum, so it's 1. So we want the permittivity to be -2. And the imaginary component is negligible, and so where the permittivity is -2 is around 350 nanometer. So this is our simple small particle approximation idea of where the plasma resonance should be. Now, if you do the full treatment, the virtue and suffering of the full treatment, and you calculate where is the extinction cross-section of a silver nanoparticle, 10 nanometer, I think, in vacuum, this is what you get. You get a giant peak exactly at 350 nanometers, right? So this is a plasma resonance. That's what we mean in our lab, at least. Now, I should add 4 caveats. This is a plasma resonance for a very small particle, for a spherical particle of a very good conductor, silver at visible frequencies, in vacuum. So, and all these 4 caveats actually have an influence as to what the plasma resonance actually will look like. Because if you take a very small particle and you make it bigger, you expect the plasma resonance to shift towards longer wavelength. And if you take a nanoparticle and instead of having a spherical particle, make it elongated, for example, then you don't have more one characteristic size, you may have 2, like the width of your nanorod, for example, and the length of the nanorod. And so you expect to have 2 resonances. And if you make the nanorod longer and longer, you expect the longer resonance to be at longer wavelength. This is kind of an antenna, right? The longer you make your antenna, the longer the wavelength at which it resonates. Also, if we go from, let's say, silver, that is a good conductor, to, let's say, gold, for example, not only that Froley condition will happen at a different wavelength, but also the losses will be more significant. And so actually, we're going to have a peak that is a slightly different frequency and maybe a little broader because the losses will be more. And finally, of course, if we go from vacuum to, let's say, water, then the refractive index will go from 1 to 1.3. The permittivity will go from, which is the refractive index squared, if you don't have losses, will go from permittivity of vacuum go from 1 to 1.7. And so, you know, you expect that plasma resonance also to shift with these changes. Okay, but this is what we mean by a plasma resonance. How can we use it? Like, why is this interesting to activate chemistry, for example? Well, there are a couple of physical phenomena. And again, they are related to the scattering and to the absorption of light. Now, the first phenomenon is related to scattering, and it's due to the fact that metal nanoparticles can focus light into sub-wavelength regions at their surface. Now, if you look at this plot, what I'm plotting is a silver nanoparticle 10 nanometer in vacuum, which is exactly the same that I calculated before. So this particle has a scattering and absorption cross-section that peak in extinction. Let's say the sum of scattering absorption has a peak at 350 nanometers, right? Just to give you a sense of comparison, this is a wavelength of 350 nanometer. That's how long it is compared to a nanoparticle that is 10 nanometers across. Now, what I'm also plotting here in the shaded blue region on the surface is the electric field intensity E squared enhancement. So divided by E0 squared, where E0 squared is the electric field intensity of the incoming light. And so I'm plotting how strong is the intensity of the field, how strongly enhanced it is on the surface of the nanoparticle. Now, I don't know if you can appreciate all the way from the back, but essentially at the surface of the silver nanoparticle, there is a small region of maybe 1 or 2 nanometers in which the electric field intensity is 450 times stronger than it is in the electric field that is incoming. So essentially, this nanoparticle is acting as an extremely powerful lens and compressing electromagnetic field intensity at its surface. Now, what can we use it for? Well, of course, for photocatalysis. Photocatalysis is a process in which you have light, and if you have absorption of light, then the probability of that of the excited state of your molecule to transition into something else is very high. But that probability is proportional to the electric field intensity through the Fermi-Golden rule. And so if we can maximize the electromagnetic field intensity, we can accelerate chemical reactions on the surface, particularly at the surface of metal nanoparticles, which are already good catalysts. So that's exactly where you want the electromagnetic field to be as strong as possible for photocatalysis. Of course, we can also use it for detecting molecules at the surface. Any molecule that, for example, gives you a Raman scattering signal, now the surface is enhancing that scattering signal, and that's what we call surface-enhanced Raman scattering. We also use it for gas sensing, because any molecule that is sitting in this extremely high field will give a strong response to the plasma resonance. And so we can kind of reverse engineer and actually learn something about what's happening on the surface by looking at the plasma resonance itself. Now, this is related to scattering, that essentially the fields that are outside of the particle. But there is also something that we can do with the fields that are inside the particle, and those are the fields that give rise to absorption. Now, how do these particles absorb light? Well, the first thing that happens is that essentially, like in a semiconductor, you have light absorption and an electron that is excited from a valence band to a conduction band. Now, here we don't have valence and conduction. It's a metal. There is a continuous level of states. And so the lifetime of this excitation between hole and electron will be very short, because these electrons can relax very quickly, the hole can relax very quickly, and eventually they recombine. So this will be of the order of a few femtoseconds, but you do form these hot electrons and hot holes. And if you're fast enough, you can use them. Now, if you're not fast enough, eventually they do relax over the course of femtoseconds to picoseconds. They bounce off and scatter off each other. They scatter off defects or phonons or the surface of the nanoparticle. And so eventually they heat up the nanoparticle. And at even longer time scales of the order of nanosecond, this heat can dissipate into the environment. And so you heat up the nanoparticle or you heat up the surrounding of the nanoparticle. Now, all these things can be used also for chemistry, because if you're quick to harvest these hot electrons, you can drive chemistry, like reduction reactions or oxidation reactions with electrons and holes, respectively. But also you can use them for the synthesis of nanomaterials if you can harvest them at the surface, or even just the photothermal effects. Like when you shine light on a metal nanoparticle, the main thing that happens is it gets hot. And so can we use this heat in order to drive chemistry, for example? And that gets close to the story that I want to tell you about the research that we did. So the physics that I want to discuss about, it's going to be very much related to how hot can we make these nanoparticles. And so let me give you a little bit of an introduction of how we conceptualize, how we can turn like light irradiation and absorption cross sections into heat. So the question that I want to answer is, how hot can we make these nanoparticles, right? Are they heating up a lot? Can we do that in our chemistry lab? Can we do it at home by shining, I don't know, an iPhone light on top of a gold nanoparticle, for example? Okay, let's have a look. Well, there are two things that happen, right? So let's make this conceptual experiment. We have a substrate, a glass substrate, for example, so a transparent one, and we put a gold nanoparticle on it. And let's say that this gold nanoparticle is by itself, there is no one around it. And then we take a light source and we irradiate this gold nanoparticle. Now, what happens is we have two contributions. First of all, the nanoparticle is going to get hot because of the absorption cross-section, right? It's absorbing light. And so the amount of heat that is generated per unit time will be given by the absorption cross-section, which has a unit of area, times the power density, which has a unit of watt per unit area, right? Depending what is the wattage of the light source that we're using, watts per unit area, you multiply by the absorption cross-section, you get the watts of heating in your nanoparticle. So these are the joules that I produce per second. Now, of course, that's not the only process, because otherwise the nanoparticle temperature would get infinitely high, and eventually we would ablate the nanoparticle away. The nanoparticle is getting hot, and by getting hot is also releasing heat into the environment. And so there is a cooling or heat dissipation rate. And this is simply given by the thermal conductivity of the surrounding environment. The larger the thermal conductivity, the faster will be the loss of heat from the nanoparticle. Mm-hmm. The area of the nanoparticle, the larger is the surface area of the nanoparticle, the easier will be for the nanoparticle to release heat into the environment. And of course, also the temperature gradient. So if the nanoparticle is mildly hotter than the environment, then the heat flow rate will be low, because we have a small gradient in an intensive quantity, so the flow of the extensive quantity heat will be very small. But if the nanoparticle gets much hotter than the environment, then we have a steep gradient in the intensive quantity temperature, and the flow of the extensive quantity heat will be very fast. Okay, and that's exactly what we want to solve for. So we want to know exactly how hot can we make this nanoparticle under a steady state illumination. And so a steady state means that the heating rate and the cooling rate need to be the same. And if we equate these two, we end up with an equation that is actually the same equation as when you solve for the voltage of a charged sphere. So the mathematical treatment of how to solve this equation is exactly the same. And you end up with this equation that says, for a spherical particle of radius r in a medium of thermal conductivity kappa, then the steady state temperature increase of that nanoparticle with respect to the environment, delta T, which is the temperature of that nanoparticle minus the environment temperature, the ambient temperature, is simply the heat generation rate divided by 4 pi kappa r. And this is true for any position just outside the nanoparticle, on the surface and away from the surface. Now, what this means is that I'm going to put this equation up here on top. Now, if you look at it, this equation depends inversely on the radius, on the distance from the center to the nanoparticle. So if I plot this delta T, essentially the increase in temperature with respect to the ambient, then delta T has a certain value at the surface and inside the nanoparticle, and then it goes down as 1 over R outside of the nanoparticle. The reason why the temperature is constant inside is simply because the thermal conductivity of metals is much, much larger than the thermal conductivity of any other material. And so the temperature equilibrates very quickly inside the nanoparticle. So we have this 1 over R, but again, we haven't answered the question, how hot can we make it in the lab, right? In order to get to a value of that, I'm going to take this analytical equation, analytical solution, beautiful analytical solution, and then butcher it ruthlessly in such a way that we can actually get a sense of what are the units, what are the orders of magnitude. Now, the first thing that I'm going to do is essentially the most difficult aspect, is the absorption cross-section. Because if we want to know how big is the absorption cross-section, we need to solve Maxwell's equations for a plane wave and a spherical particle. So I'm going to use an approximation that says, well, let's treat this nanoparticle as microscopic objects and say that their absorption cross-section is actually just pi r squared. And this is mostly true, or in terms of order of magnitude. Actually, this nanoparticle can have larger cross-section than pi r squared, but just for orders of magnitude, let's keep it there. And that means we can simplify the radius and the pi. We get Ri over 4 kappa. The thermal conductivity, for example, of water, which is the medium that we use a lot, is 0.6. So 4 times 0.6, that would be 2.4. But again, we are talking about orders of magnitude, so I'm going to put that as 1. And so essentially, the order of magnitude of the temperature increase that we can generate is given by the radius of the particle times the power density in watt per unit meter, per square meter. Okay, let's go back to our conceptual experiment. We have a substrate, we have 1 nanoparticle, and we shine light on it. Let's say that the nanoparticle has a radius of 10 nanometer, and let's say that we have 100 milliwatt on it. I'm choosing 100 milliwatt because we have a laser that, shoots out 100 milliwatt of green light, continuous wave. So I know that that's possible and easy and cheap to get in the laboratory. Now, if you don't focus the laser, so you are doing what we call an ensemble experiment, because in principle, you can illuminate a lot of particles at the same time. Then the beam spot, for example, could have a size of about a square millimeter. This is typical for a laser, CW laser coming out of the box. And 1 square millimeter, 100 milliwatt, that means 10 to the 5 watts per square meter. And so if we now multiply this 10 to the 5 with the radius of the nanoparticle, which is 10 nanometer or 10 to the minus 8 meters, then we get a delta T of a millikelvin. So I'm taking 1 gold nanoparticle on a substrate. I take a 100 milliwatt laser, don't focus it, shine on it. I get a millikelvin of temperature increase. Nothing, right? It doesn't get hot at all. But now I take a good objective lens, a good microscope, and I focus the laser onto the nanoparticle. And let's say that I can make a diffraction spot that is about 1 square micron. This is typical. If we use visible wavelength, that's rather easy to make, 1 square micron of beam spot. And so this would be a single particle experiment. Now we are focusing the laser on our ideal nanoparticle. And if I go from 1 millimeter to 1 square micron, I'm gaining in 6 orders of magnitude in irradiation intensity. So going from 10 to the 5 to 10 to the 11. And so I'm also gaining 6 orders of magnitudes in delta T. So now if I have 1 nanoparticle, a 100 milliwatt laser, and I focus it on the nanoparticle, I can blast it away. I can ablate the nanoparticle thousands of degrees, right? So in principle, yes, it is possible to activate chemistry on single nanoparticles. Now, this whole experiment was when you have 1 nanoparticle, but there is another way in which we can make our plasmonic materials very hot. And that way is by not having 1 nanoparticle, but having an array of nanoparticles. Let's say many nanoparticles being illuminated at the same time. And I can show you a solution of how hot it gets if you have like a square array of nanoparticle. It looks something like this. So the delta T local that I'm plotting here is exactly this delta T that I'm plotting here. So each nanoparticle will be getting hot by a certain amount. However, now there is the effect of the collective heating. So if we are all nanoparticles sitting under the 100 milliwatt beam, then I'm getting hot by my delta T local, but also other nanoparticles are getting their delta T local. And so the ambient temperature overall is increasing, right? And how much is it increasing? It depends on the radius of the nanoparticle. Again, it depends on the size of how many of us are illuminated. The more of us are illuminated, the hotter it gets in the ambient. And of course, it also depends on the interparticle distance. So if the smaller the interparticle distance, the higher will be this collective heating. And if you redo this same experiment, so this would be for a beam spot of 1 square millimeter, but now instead of having the 1 square millimeter hitting one nanoparticle, let's assume that we have 1 square millimeter hitting our nanoparticle of 10 nanometer of radius, but then there is a nanoparticle every 50 nanometer. So there is an array of nanoparticle with an interparticle spacing of 50 nanometer. If you plug in the number into this equation, you'll see that delta T collective is actually 4 orders of magnitude higher than the local. So now, if we have 1 millimeter beam, we don't focus it, but we have enough particles, each nanoparticle will be only a millikelvin hotter than the environment, but the environment is now 10,000 times hotter than it used to be. So we can heat up our nanoparticles either by focusing on a single one or by having more than one under the beam. And I'll show you what consequences these has in both cases, so ensemble experiments and single particle experiments. Now, I should add a caveat, because I gave you this talk yesterday at the Photonics Center, and there was a very good question about, okay, but what happens with pulse laser? And everything that I've said so far is about continuous wave illumination, because I've defined a steady state temperature. Of course, under pulse illumination, the temperature profile cannot be defined as a constant, so the conditions change dramatically. Okay, let me get to my story, and I'm going to tell you how it all started and essentially where we are now, and what kind of questions we tried to solve. And now there is a little bit of chemistry, but very little. So I hope you'll forgive me and maybe follow me throughout the path. So it all started when I was a postdoc in California, and when I was there, I started reading these papers that were very exciting to me. As a chemist, and I love nanoparticles. I love mixing liquids in the lab and actually making nanoparticles. So what these people were doing, they were taking like silver nanoparticles, these little spheres of silver, and then they were shining light on it. And after shining light, the silver nanoparticles would evolve and grow into silver prisms. Very different shape, very different sizes. And not only that, but actually the final size of the silver prisms dependent on the wavelength of the light that they were using. And to me, this was very, very exciting. That means essentially that not only you're running a reaction, but actually you're adding photons into your reaction. And depending on the color of the photons you're using, you get different nanoparticles. So light becomes really a chemical ingredient. And I wanted to understand what is going on. Now, I was very skeptical. And actually, so this is the plasma resonance wavelength. If you start from silver nanoparticles, it has a strong peak around 410, 420 nanometer. And if you shine a laser of different wavelengths, you get different prisms that grow. And as they grow bigger, their plasma resonance shifts towards longer wavelength. But actually, let's take the example of the 470 nanometer. This is 470 nanometer. Essentially, what's happening is these nanoparticles are growing and growing, and the plasma resonance is moving towards longer wavelength until, so I'm a silver sphere, I have a resonance of 420, and I'm hitting with a laser at 470, and then I'm growing and growing and growing until the resonance essentially goes past me. My resonance goes past the laser, and then I'm not growing anymore. And so I thought, okay, I know that you're using a chemical, which is called ascorbic acid, that only works at 60 degrees or above. So if you run these reactions at room temperature, they don't work typically. And so I thought, okay, this must be heating, right? They're shining a laser through a suspension of nanoparticles. They're just heating it up. And by heating it up, they're activating this reducing agent and activating chemistry. So the hypothesis that I had when I started my own research group was, okay, all plasmon-driven nanoparticle synthesis are due to photothermal activation of the reducing agents, in this case, ascorbic acid. This is only heat. And that's exactly what I believed. And so with my first PhD student, we said, okay, let's try to prove it. And in order to prove it, we said, okay, well, first, before I go there, I should mention a caveat. Like, I'm considered an expert in plasmonic chemistry, and Niels Bohr defines an expert as a person who my hypothesis, now you know where I'm going with that. Now, the question is, okay, you're thinking that if you have a suspension of nanoparticles and you shine light on it, it's all temperature. So why don't you measure the temperature, right? Why don't you put a thermocouple in your solution and just tell us how hot it gets? And the problem with that is that First of all, these nanoparticles, they scatter and absorb a lot of light. And so the temperature on one end of the solution might not be the same temperature on the other end. Also, thermocouple are light sensitive. Also, this gradient in absorption gives you a gradient in temperature and gives you convection flows. So it's very difficult to actually say how hot it gets. Maybe when you turn off the laser, then you can put a thermocouple in, but it's never a direct reading. So we wanted to study a model system under controlled experimental conditions. Here's the physicist in me that is kind of arguing against the chemist. I don't want to mix stuff. I want to have a very controlled system. I don't know exactly what's going on. So we developed a synthesis in which we did the following. So we synthesized some gold nanoparticles. In fact, we chose gold 18 nanometer in size. The reason for it is because they become extremely hot. This is the best size that you can have of gold if you want to make it hot under the, green laser irradiation. So we wanted to demonstrate that everything was heating. So we thought, okay, let's take the nanoparticles and heat the most. And then there were a couple of reactants. There was silver ions in solution. There was the ascorbic acid, which is the reducing agent. So we need the reducing agent to get silver and actually make it into a silver shell. So if you leave the reaction at room temperature, nothing happens. The gold remains naked. But actually, if you heat up a little bit, then the ascorbic acid is reducing silver and forming a shell of silver, metallic silver around the gold nanoparticle. Now, the way we can study that is by looking at the plasma resonance, actually doing in situ optical spectroscopy. So you go from gold nanoparticle and end up with gold coated with silver. Essentially, you go from a plasma resonance in the green around 542, and if you wait 5 hours at 65 degrees C, then you see that this plasma resonance becomes larger, stronger, and then there is a shoulder also happening at the blue side. And we can model this with me theory, which is the exact solution to light scattering and absorption. So we know exactly what's happening, and we know how fast. And we can also confirm that using EDX. So we see these gold core and silver shells. Very well. Okay. Not only we know what's happening, we can also control the speed at which it's happening if we run the reaction in the dark at different temperatures. And in fact, the chemical reactivity is typically it increases exponentially with temperature, and we plot it in terms of an Arrhenius law. So the logarithm of the rate as a function of the inverse temperature should give you a straight line, and we do that within, between 35 and 60 degrees C, and we get exactly a straight line. So now we have actually calibrated how fast this reaction goes at different temperatures. And the next step that we did is, okay, now let's not change the temperature. Now we shine light on it at room temperature. So we put it in our setup where we can both do spectroscopy in one direction, but also we have laser irradiation in the other direction. And we're actually using a green laser at 532. So we are really heating the plasma resonance of the gold. So in principle, we should be heating up the gold very much. And when we do direct experiments, we also vary the laser power. So we increase it between 250 and 450. And again, when we plot the log of the rate as a function of laser power, we see this trend. Now, I want you to remember just one number, that if you look at the rate, essentially the rate that we get at 400 milliwatts of laser irradiation is the same rate that we get around 50 degrees C. Okay. So when we shine a laser at 400 milliwatt, we see a reaction going as fast as when we heat up to 50. Okay. Now the question is, how hot is it when we shine 400 milliwatt? Is it at 50 degrees? Because if it's at 50 degrees, then everything is thermal, and we have proven what we wanted to prove. Now, in order to understand how hot it is, what we did was actually modeling exactly the reaction that was happening. So this is our little cuvette. It's a slit cuvette. It has this kind of dimensions. The wavelength that we are using is 532. We have 400 milliwatts, and the spot size is 1.5 millimeter. So we know exactly the illumination conditions. And we also know that our gold nanoparticles are 79 nanometers across, so we can calculate the absorption cross-section and the scattering cross-sections. And essentially, we can model exactly using a Monte Carlo model, the light propagation into our system. And we can calculate how much heat is absorbed in each voxel of our volume. And the heat absorbed has this relationship that we took from a paper from Rice University. And so essentially, we're calculating the amount of light power that is absorbed in each voxels in which we are breaking up our reaction volume. And to visualize it, forget about the equation. The important thing is that it looks like this. So this is the amount of heat that the power that is dissipated per unit volume. It's about a few watts per cubic centimeter. But the important thing is that if the laser is entering from the left, a lot of heat is being absorbed at the entrance. nanoparticles that are absorbing and scattering light that essentially light doesn't go through and is quite absorbed. So we modeled this through Monte Carlo. The first thing that we notice is that heat generation is highly inhomogeneous. So the particles that are seen the laser face front and the ones that are all the way in the back will be heated differently. The other thing is that, again, we have a non-focused laser, gold nanoparticles. The temperature increase locally for each gold nanoparticle is only a few millikelvins, right? That makes sense. Dimensionally, we saw before that if you don't focus, the delta T that you can get is only millikelvin. However, that is if you have one nanoparticle. Now we have many in solution, and so maybe these collective effects are heating up. But in order to understand the collective effects, you actually also have to understand what is the convection flows that are in our solution. And so we use COMSOL simulation. Actually, we collaborated with a group that does COMSOL simulation. And what they notice is that heat transfer is actually dominated by convection. And you can understand why. I mean, if you're heating up only one side of the cuvette, this side will get hotter and less dense. It will go up. This side will flow down. And then eventually, over the course of a few minutes, there is this convection flow that is circulating. So heat transfer is strongly influenced by convection. But also, if you calculate the total temperature, because that's something that you can do in COMSOL, it comes down to 37 degrees C. So the average temperature in the cuvette is about 37 degrees C, and the maximum temperature is around 40. And this solution had the same rate of the solution in the dark heated at 50 degrees C. So we expected a temperature of 50 degrees C if we wanted to be exactly equal, but actually this is much colder. And so in the end, we wanted to prove that everything is temperature, and we couldn't. In fact, if we put in how much is temperature, we can only account for about 30% of the reaction rate. 70% of the reaction rate must be something that is non-thermal. Also, this fraction depends on how much we illuminate. And in fact, if you look at the quantum efficiency of this process, taking a photon and essentially reducing it into a silver atom on the surface, the quantum yield is abysmally low. But the question is, okay, first of all, it's not all heat. We tried to make it as heating as possible, and we could only understand 30% of what was going on. So first of all, we were wrong. And second of all, actually, we published this paper. Let me show you. I don't know, sometimes it blocks. So we published this paper in 2018, and we called it Quantifying Photothermal and Hot Charge Carrier Effects in Plasmon-Driven Nanoparticle Synthesis. And we're very happy because a couple of months later, the group of Naomi Halas, they published a paper in Science almost with the same title, Quantifying Hot Carrier and Thermal Contribution in Plasmonic Photocatalysis. And so we were going from nanoparticle synthesis, they were studying photocatalysis. But essentially, the research question was the same. How hot is this getting? And are the effects that we are seeing only due to heating up? And we tried our best to prove it, and we couldn't. But then someone from Israel, Jonathan Sivan, he read this paper by Naomi Halas and was very angry at these results. And so he published a comment on quantifying hot carrier and thermal contribution. And then Professor Halas published a response to the comment to quantify the hot thermal contribution. And so essentially, this was a hugely heated debate in the field, like how hot are we making these nanoparticles? I'm very happy that Jonathan Sivan did not write a comment on our paper. And in fact, he likes our paper very much. He says, actually, we did the right thing. So I'm not on his bad side. But this question of how hot are we making it and whether this is all thermal, was a hotly debated topic. And I think we tried our best to prove that it was all thermal, and we couldn't. So then the next question is, okay, what is it that is non-thermal? Like only 30% of what's going on can be attributed to temperature. What is happening otherwise? Like what other effects are there? And so the first hypothesis, back in 2018, a lot of people were talking about hot electrons. So you shine light on a metal nanoparticle, you're shooting out these hot electrons outside of it, kind of like a photoelectric effect. In fact, the solution to understand this hot electron injection is exactly the Fowler equation, which is the equation that you use to characterize photoelectric effect. So we thought, okay, the non-thermal effects are due to the ejection of hot electrons into the silver ions. And so we have silver ions on the surface, and there is an electron jumping out of the metal and reducing that silver ions into silver. Now, remember, I'm an expert in plasmonic chemistry, so I've made every mistake in the field, and you'll see where this goes. So this experimental design was like, okay, let's try to prove that that is hot electron, that these electrons are shooting out of the nanoparticle. And the way we thought of proving it is using, instead of spheres, using nanoparticles that are elongated. And so these nanoparticles are actually having two resonances, one along the length of the rods and one along across the rod. And so we thought, well, if we shine corresponds to the resonance across the rod, we should be shooting electrons out of the sides, and so maybe forming silver on the sides. And if we shine a green laser, and so which corresponds to the resonance along the rod, maybe we're shooting electron out of the tips, and so we should be growing silver on the tips. So if these are hot electrons that are plasmonically generated, we should be having differential growth. And then we did the experiments. And actually what happens is that if you shine the green laser, something happens everywhere. And if you shine the red laser, absolutely nothing happens. Not a single thing. It's like you're not even shining light on it. So maybe not hot electrons. And then we say, okay, now we need to, do a more systematic study and trying to understand what's going on. So let me show you what we did. So we did the same exact reaction. We have a gold particle, silver, and we grow a silver shell. In this case, it's not a sphere, it's actually a rod. And this rod actually goes through several steps. You start from a rod, then you form a rod with a thin shell. Then you have a rod with a box of silver, about 4 nanometers in thickness. And then eventually this box grows anisotropically. You get a thick shell around it. And we can follow this precisely spectroscopically because the longitudinal peak of the rod is very sensitive to these thicknesses of the shell. So you start with a little blue shift, and then it goes back to as a red shift, and then go back as a blue shift. So essentially, by looking at how the plasma resonance shifts, we can follow this chemistry. So we run this reaction both in the dark and under laser excitation. This is the comparison between the dark experiment. This is the extinction cross-section as a function of time over the course of 1 day. Not much happening in the dark. And then we run 730 laser through the cuvette, and not much happening Not much is happening either. So in the dark or under 730 irradiation, we are exciting the plasma resonance right here at this peak, and nothing happens. And then we run the reaction on the green laser irradiation at 532, and then you see this happening very quickly. And so note that we modulate the laser intensities to have the same total absorbed power. So we shine the red laser and the green laser, but we modulate the laser power so that the total absorbed power is the same. So the thermal effects will be the same. So the difference cannot be due to thermal effects. So in fact, if you plot the speed at which this this peak changes as a function of time, logarithmic time, you can see that 730 and dark are almost the same speed, and 532 is actually much faster. We can also look at how much faster it is. And in fact, it's like this. So if you look with respect to the dark experiment, at the beginning, when you shine the green laser, it's very quick. And then after you form this 4 nanometer box, the enhancement kind of plateaus. So at the beginning, we accelerate the reaction very quickly, and then it dies off. And this gave us a hint as to what was the actual mechanism behind. And the hint came from a theoretical paper by Professor Bernardi at Caltech, where he says that the plasmon that have a wavelength that is shorter than the interband threshold, which means a photon with an energy that is larger than the interband energy transition, leads to hot holes in the D states of gold with sub 5 nanometer mean free path. What is it? What does this mean? Gold is a metal that has a Fermi level in the sp band, and then there is a d band of electrons, about 2 electron volts, in fact 1.7 electron volts below the Fermi level. And if you have photons that have enough energy to fish into this d band, what you will end up with is an electron that is close to the Fermi level and a very energetic hot hole in the d band. However, the d band of gold is very flat, and the mobility of this hot hole is extremely low. The effective mass is very large. And so this hole cannot travel very fast. In fact, within 4 to 5 nanometers, it recombines. And so what we think is, since the interband threshold for gold is 730 nanometer, if we shine light with 730 nanometer, we're not fishing any of these hot holes. We're not creating any hot holes. There's no enhancement of the chemistry. But if we shine the green laser, now we're forming a lot of these hot holes. We can enhance the chemistry. However, these hot holes don't move very far. And so if we grow a shell of 4 nanometers, essentially we kill the effect. So we think that that's what's causing this enhancement, is the hot holes in the d band of gold. We actually proved it we calculated what is the amount of absorption within the 4 nanometers of the gold nanorods for these 4 scenarios. And if you look at the total amount of power that is absorbed, it actually increases as you make the nanorod bigger. However, if you look at the amount of power that is absorbed in the outermost 4 nanometers of these nanorods, actually it's very high at the beginning. And then it goes down because essentially all the power is absorbed in the gold. And as you grow a thicker silver shell, you don't get any more absorption. And so it follows the experimental trend. It's hot holes. Okay, now I've shown you kind of the path that we took in order to understand, what was the mechanism of a lot of it, and we learned also how to handle heat. And so the last thing that I want to show you is how can we use photothermal effects on single nanoparticles? Because so far everything was in solution, right? This was very chemistry oriented. But now let's consider that we have our substrate and we have a gold nanoparticle, for example, and we focus a laser onto it. Can we heat it up and can we activate chemistry on it? And grow, for example, stuff around them? Now, we're not the first one to try. Many people have tried to grow, to use photothermal effects, so light into heat effects, to grow nanostructures, and they've failed. Well, not failed, but let's say typically their nanostructure, it's very hard to distinguish between heating and maybe non-thermal effects. The structure that you make are typically hundreds of nanometers, if not several microns. It's also difficult to control the size and the shape. And we want to try to see whether we can heat up a single nanoparticle and grow a shell of any material with any thickness that we want. Okay, so the way we did it is using microscopy. So you take a little piece of glass and you put gold nanoparticles on top. And then we have white light that is reflected by a dark field reflector. The way this works is that it takes a beam of light and it only reflects a hollow cylinder of light. And we run this through a dark field objective. So this hollow cylinder of light is being focused onto our sample. And then if there is nothing that scatters here, if there is a perfect flat interface, essentially the light is not picked up by the objective anymore. So it's only reflected in the outer part, but the light that is being picked up by the objective is nothing. So if you have a perfectly flat and clean interface, you see black. But as soon as you put a speckle of dust on your substrate, or let's say a gold nanoparticle, then you are going to see the light that is scattered by your little speckle of dust or your gold nanoparticle. And if your gold nanoparticle scatters a lot in the green, essentially that's what you measure, and you measure the localized surface plasmon resonance, or LSPR. So we can do scattering spectroscopy of single nanoparticles. Now, with the same setup, we can actually switch it from white light into a laser. And so instead of having a dark field reflector, now we put a 50% mirror, and we focus our laser onto the nanoparticle, which we have identified. And at the same time, we can also do more. We can flow some reactants so that we can heat up this nanoparticle and heat it up and maybe grow something around it. And at the same time, measure the photoluminescence out of this nanoparticle, which is the light that is being inelastically scattered. So we can look at the anti-Stokes or the Stokes inelastically scattered light. So this is the reaction that we chose to start with. We have gold nanoparticles and we wanted to grow Syria shell. This is actually a reaction that happens in normal chemistry. You mix reactants and you put in, you heat it up. So if you heat up at 90 degrees C for 5 hours, you get the Syria shell around it. So we thought, okay, this is a perfect thermally activated reaction. We should work by shining light on a single nanoparticle. So then this is what we did. We took a gold nanoparticle. It looks green in dark field, right? Because everything is dark except the little speckle of gold that scatters a lot in the green. And then we shine a laser for 15 minutes, and then we take another dark field scattering spectrum, and it looks red. And so when you look at the spectra, you go from a gold nanoparticle that is green, has this scattering peak at 550 nanometer, and then after 15 minutes of irradiation with the laser, we grew a Syria shell around it. And so the nanoparticle, the plasmon resonance redshift, and it becomes much stronger. And we can confirm that we are growing Syria by growing doing the same process on nanoparticles that are on a transmission electron microscope, and then doing EDX analysis over the core shell nanoparticle that we created. So we did a lot of experiments, and we showed that actually the amount of heating controls the final thickness of the Syria shell. But there is more that we can do, because this is only before and after. And the question that we had was, okay, but what's happening during laser irradiation? How is this Syria shell growing? Is it growing linearly? Is it growing very fast at the beginning and slower at the end. So the way we did it is by collecting inelastic light scattering. Now, in the inelastic light scattering, or the photoluminescence of the gold, there is many contributions, because everything inelastically scattered light. Gold itself has a strong photoluminescence, but also the quartz substrate will have a photoluminescence. There is surface enhanced Raman scattering from molecules that might be on the surface of the gold. And these contributions are very difficult to decouple. So if you measure the PL, you'll see a very strange PL that doesn't tell us much. But then we know that these basic contributions that are always there, they are always there throughout the whole reaction. And so we can subtract any spectrum, we can subtract the first spectrum from any spectrum. And if you look at the delta PL, then we get two peaks. And this peak is actually moving towards longer wavelength. And so we also know that the PL scales with the scattering cross-section. So essentially, we know in real life how fast is the Sirius shell growing. Nanoparticle, and we are shining 532 nanometer on top of it, heating it up. It's heating up and growing a Sirius shell, but while it's growing a Sirius shell, it's also shifting plasma resonance. And so the 532 nanometer eventually doesn't heat up anymore, and so it's self-limited. Now, since this is purely thermal, we can grow anything in principle. And so we proved it. We say, okay, we can grow Syria for sure, but then we grew also zinc oxide, we grew zinc sulfide, and in fact, we can do that on the same substrate. So this is a dark field scattering image of several gold nanoparticles. And then Rifat, my PhD student, said, okay, let's try to grow Syria here, zinc oxide here, and zinc sulfide here by flowing different chemicals and shining the laser on different particles. And that's exactly what it did. So in fact, we can grow any core shell semiconducting materials or over individual nanoparticles, while, for example, a gold nanoparticle that is sitting right next to it is completely untouched, because we're only really growing where we're heating up with the laser. Okay, so that brings me to the end of my talk. What did we discuss? Well, I showed you a little bit about how we use plasmonics and how to activate chemistry, and also how the plasmonic properties depend on the size, the shape, and the composition and the environment. And this can control the resonance frequency. Also, I showed you how we can use it for chemical activation and sensing through the fact that they focus light and also they generate heat and charge carriers. And finally, I've told you a little bit about the story of how we try to understand what was going on when we were trying to grow core shell nanoparticles, and how many wrong hypotheses we made, but all the learned lesson that we got on the way. Before I thank you, Ferry asked me also to put this poster here. I'm going to be speaking about effective PowerPoint presentation tomorrow. So this is a lecture that I give typically to my students. So it's going to be the first time that I'm actually going to give it to colleagues. And I hope you'll enjoy it as much as I enjoyed giving it. And I would love to hear feedback from you on how to give effective PowerPoint presentation. I know that this was a very long lecture. I'm not used to it, but of course, giving strong PowerPoint presentation is crucial today, right? At conferences, at job interviews, and anything, if you want to shine, you need to be convincing. So I would love to share a little bit of the experience that I have, and maybe hear the feedback that you have. And so I'm going to give this presentation tomorrow at 3 p.m., right? Is it in this room? Okay. Okay. And with that, I would like to thank you.
Yes, thank you very much, Andrea. It was a really fascinating talks, and what's amazing about this is how usually researchers do their work. I mean, they try to answer one questions, but then they come another questions, but then eventually over some years you really cover the whole aspects of just one simple questions, right? I mean, here he just talk about how you can use light to drive chemistry, but then on during the way he found a lot, he found new things, he found many things. So this is really the spirit of research. So I will open the questions for you guys. So this is really your chance. If you are, if you want to know more, if you have some questions, some doubts, or you want to have comments on Andrea's presentations today, like then he will respond to your comments, and then there will be fight. So if there are any questions, and online, I think we have what, more than 50 participants, yeah. So they are watching. 62 now. So maybe those online, if they want to ask question as well, maybe you can type there, they can put the questions. So maybe I'll start with one question, Andrea. So I have been trained, making nanostructures, but using photolithography or lithography, right? But then I move now to Indonesia. I think if we want to continue that path, it will be difficult, if not impossible, to continue that one. So I'm really interested to also, and I have to work now with probably colloidal synthesis, right? And these are really wonderful. I mean, yesterday we talked with colleagues from Brin that everything, the setup is everything. Basically, we have everything here. But then the mastery of this colloidal synthesis, probably that's the one that I don't have. So my question is really simple. When we try to functionalize these nanoparticles, let's say, for example, the metal nanoparticles with some other substances, the oxides or metals, right? You grow something on it. But then we know that these nanoparticles are basically covered in surfactants. So I cannot really wrap my head around it even until now. Like, how do you then remove the surfactants? Will they still stay there? Because I can imagine like the surfactant is really sticky, so they don't want to get moved. But then how can you, cover something surrounding it? So maybe that's my question.
Oh, that's a great question. It's a very chemical one. I mean, surfactants are there to prevent nanomaterials to essentially collapse onto each other, right? Nanomaterials don't like to have high surface, right? Materials in general don't. You pay a huge price in order to create surface, and the reason why you pay it is because surface is where the magic happens, and that's exactly what you want. Surfactants, however, are not like a fixed molecule that is just covalently or strongly bound to the surface. Depending on the type of surfactant, that can be the case, particularly if you have like thiol base or sulfur terminated organic ligands on top of gold, then there is a covalent bond between the sulfur and the gold, and it's very difficult to get rid of it. In the case of the surfactant that we use in this synthesis, we are using like an amine-based surfactants, and they have a very dynamic coverage. So you always have a balance, a dynamic balance between the surfactant attaching to the surface and then leaving the surface. And that leaves enough time and space for reactions to occur. But it is crucial, and it's probably the least acknowledged huge factor in catalytic rate in plasmonic catalysis, particularly in solution. This is something that has been overlooked for way too long. And so what we do typically is to buffer and control the concentration of the surfactant and make sure that when I'm comparing, for example, the rate of two different nanoparticles, the surfactant concentration is exactly the same, because that's going to have a huge impact.
I have a following question on that one, because obviously it's difficult to synthesize probably our own metal nanoparticles. So the plan is, my recent plan is basically just to buy this commercially available nanoparticles, for example, golds, but then they come with different surfactants, right? Probably a CTEC, CTEP, and so on. So can we do all of this shelling reactions with any of these kind of surfactants, or it has to be like what you said, like amine base, amine base, or something like that?
Yeah, the beauty of buying nanoparticles is that they're fantastically narrow size distributed, so you can get exactly the size that you want. The problem with that is that the way they maintain this size distribution very constant is by adding a ton of surfactants. And in fact, not only they add a ton of surfactants, they also don't tell you what it is because it's proprietary. They often have patents on the mix of surfactants. So you never know exactly what's on the surface. So my recommendation would be to buy them if you want, but then centrifuge them down and wash them with something else that you know.
Okay, so basically replace the surfactants.
Yes. Replace the solvent and the surfactant with a solvent and surfactant that you actually can control.
Okay, thanks a lot. So is there any following questions? Yeah, Rizwan.
First of all, thank you very much for giving this opportunity to ask some questions. Professor, I have a question that, like in my bachelor, when we were dealing with the nanomaterials for the photocatalysis purpose, so in that we deal that like how to deal with the charge carriers from the valence band to the conduction band through the light. But here, like you talk all about the hot charge carriers. So is there any role, like in that we were dealing with the oxidation and reduction reaction for the water splitting. But here you all talk about the hot charge carriers. So is there any role of these hot charge carriers in that photocatalysis or hydrogen production?
For hydrogen production and water splitting, let's say. Yeah, there is definitely studies. Actually, the first studies, I think it was done by Martin Moskowitz at Caltech. There is a Nature nanotechnology where they're using gold pillars that are coated with a semiconductor or insulator layer. I want to say it's alumina, but I don't exactly remember. And this paper, they demonstrate that all the photon and essentially only the photon energy is used for splitting water into hydrogen and oxygen. That's just one of the probably hundreds of papers on water splitting. So the community, particularly the community in the western part of the United States, was working a lot on water splitting in the past 10 to 15 years through this Joint Center for Artificial Photosynthesis Initiative, JCAP, which was a collaboration between Berkeley and Caltech. And they looked at plasmonics a lot. In the second round of funding from the government, they actually moved from water splitting to carbon dioxide reduction, which I think it was only political because they needed to get an extra $1 billion for funding. But actually, it's probably a bad idea to go to CO2 reduction, because CO2 reduction is an 8-electron process. If you want to go, for example, from CO2 to methane, right, you need 8 electrons to reduce carbon, because it goes from +4 to -4. And so water splitting is much easier. And in fact, once you form hydrogen in a clean way, you're almost half the way, right? If you have CO2 and hydrogen, you can make anything that you want, essentially. In fact, there is this really cool company. I just learned this a few months ago. I love this story. They are producing vodka in New York, so alcohol, so ethanol. And the way they're doing it, they call it green vodka or air vodka. Now, they're not only producing alcohol for consumption, they're also producing perfumes. But the interesting thing is that now their technology is explored by the LaGuardia and JFK airports to produce bioethanol for fuels for airplane. The way they do it is they do water splitting using renewable energies. For example, I don't know, photovoltaics and wind turbines, they split water, produce hydrogen, and then they buy CO2 bottles from plants that, for example, do ethanol or corn fermentation, or plants that produce CO2 in any other fermentation. And this CO2 is extremely cheap. Typically, they use it just to make sodas. They don't know what to do with it. And so they can buy this CO2, they take the green hydrogen from electrolyzers, and through their catalytic process, they can make ethanol from CO2 and hydrogen. That's a beautiful idea. Much simpler than going, than run an 8-electron reactions directly on your little plasmonic nanoparticles to take CO2 and make methane, which is exactly what I have proposed to my funding agency to do, to take CO2 and make methane, by the way, and I got funding. So I still use the narrative, but I think hydrogen splitting has been the main focus of the community of plasmonic chemistry, in fact, for energy application.
Thank you very much.
Yeah.
One first from the audience online. Yeah, there's a question from Muhammad Sujak. I think it's a graduate student from Korea now. So he said that, could you please talk a little bit briefly about periodic plasmonic array? He will.
Briefly. Yes. Okay. I can give you a sense. I'm going to look there. I'm assuming that that's right. So today I have given you an introduction into light scattering and absorption by nanoparticles. There is a condition, and I've shown you that for many plasmonic nanoparticles, this peak in light scattering happens in the visible. Now, suppose that I am a nanoparticle and I'm scattering in wavelength that is, let's say, 500 nanometers. And now suppose that exactly 500 nanometers away from me, there is another particle identical to me. And so the light that is scattered from me can constructively interfere with the light that is scattered by my next particle and my next particle and my next particle. And so the signal of scattering, essentially the probability of that wavelength to go through us is much, much smaller, because we all interfere constructively to scatter that wavelength. And so instead of having these very broad plasmon resonances, we can get extremely sharp collective resonances which, for example, we use to, we just published a paper in Nature Communication last year with Dr. Ferry. We used it for gas sensing, because when you have a high Q factor of your resonance, your sensing capability becomes larger, right? If you have a resonance that is very broad, if it moves a little, you don't see it. But if you have a resonance that is extremely sharp, if it moves the same little amount, you will see it very, very nicely. So these emergent phenomena through collective scattering are really interesting for us, both from a fundamental but also applied point of view. I hope that's going in the direction.
Yes, that's a perfect brief explanation of plasmonic lattice resonances. So yeah, it's rather not really new, but I think people are now capitalizing on the effect for many applications, including sensing and also something else.
Yeah, we can also play not only with the wavelength, we can also play with the angle. And so, for example, you can take a lattice array that scatters only in one direction, or couples to light only in one direction. And so you can use it for like satellite communication, where you have specific angles of diffraction of light that is maximizing one direction. Yeah.
Yep. Is there any questions? Yes, Prof. Vivi.
Dr. Baldi, it's very nice presentation. I have a little experience about metal nanoparticle. As far as I know, there is something interesting properties from metal nanoparticle for photocatalysis application. There is special interesting properties, that is the reactivity is depend on the arrangement of atom in the surface. So we call it high energy facets because it is more reactive than the other facet, and also the arrangement of alloy metal atom. I think it is interesting if we combine with the optical shape and also the composition about the atom in the surface. What do you think about this? Thank you.
Great question. Thank you so much. I want to, yeah, I definitely agree with go back to this slide just to show that the kind of fundamental mechanisms that we try to study for nanomaterial synthesis for the shell growth in other groups and also in our group now, people have been studying for photocatalysis, right? So this is a fundamental field. Like if we can use sunlight, for example, to drive chemical reactions that are, for example, water splitting, CO2 reduction, or ammonia synthesis, CO oxidation for pollution mitigation, that would be a fantastic dream. And so particularly in the group of Naomi Halas, Peter Norlander, maybe Sulio Linic, also in Michigan, there has been a lot of studies in photocatalysis. What you mentioned is interesting because you say, well, we really need nanoparticles that are much smaller than the particles that I've shown so far, right? I was talking about particles that are in the order of tens of nanometers, maybe 80 nanometers. But if we want metals to be catalytically active, we want them to have a very high surface area. We want them to expose low coordination surface facets, which are very highly energetic and therefore can catalyze reactions very properly. Then our nanoparticles need to be small. So the first paper that showed like size dependence catalysis in gold, for example, was using gold nanoparticles that were sub 5 nanometers. And in fact, if you look at the turnover frequency in catalysis, so how many products you're making per site per second, as a function of size of your gold nanoparticles, as you make it smaller and smaller and smaller, the turnover frequency goes up. Precisely for what you were saying, you're exposing low coordination facets, high energy facets. But so how do we reconcile that we want these low coordination facets of extremely tiny particle, maybe 1 nanometer across, maybe even less, maybe like gold clusters, like almost quasi-molecular orbitals, with the fact that we need them to absorb light to drive this chemistry through plasmonics. And what people have started to do, and we have also started to do, is to make antenna reactor complexes in which you have a plasmonic nanoparticle that kind of sustains the light absorption and scattering job because it's big enough to interact strongly with the electromagnetic field. And this plasmonic nanoparticle is decorated with metal co-catalysts that are tiny particles that have these high energy surface facets and actually transfer they are the ones that are doing the catalysis. And so the resonance the interaction with the electromagnetic field goes through the antenna, but this interaction with the electromagnetic field is transferred to these co-catalysts that are sitting on the surface that are kind of feeling the same resonance that is driving the big antenna, but actually they're also doing the catalysis through these high surface facets. So there is ways of creating this hierarchical structure where you have both of the worlds combined. Thank you.
Yeah, I think this antenna reactor concept has been patented by Naomi and Nordlander, and they are actually now making a company out of this. So they create a very cheap photocatalysis system just using LEDs, and they can produce many different valuable chemicals. So we'll see in years how it will go.
The company is called CZG.
CZG,
It's impossible to pronounce and write.
Sajajai or something.
SYZYGY.
SYZYGY, yeah. CZG. So is there any question? I think Mr. Aziz must one questions. Please ask difficult questions.
I don't know much about this, so I just want to ask probably something that to you maybe a very simple question. Oh, by the way, my name is Aziz Majidi. My research field is actually theoretical condensed matter physics, and I kind of like to extend my research area to something new that I didn't know before. I want to learn. So this is one of the things that I like also to start looking at. From your presentation, I think I've seen the picture that we have nanoparticles. We utilize laser to make the nanoparticles become hot and make the surrounding temperature also increase. And from the theory that you described, looks to me that you use a lot of simplifications, like for instance, assuming the area or something that actually has to be calculated using the cross section, right? Then you use a simple just the physical cross section. So what I'm wondering is how much do we actually have to go into the more rigorous calculations? So I suppose that when you use formulas, those are from Rayleigh theory, right? Rather than question is how much we may actually go better if we go from Rayleigh theory to me theory.
Yeah.
And I actually really want to know what more aspects that you probably haven't explored, but you have seen potential, exploration in that area, so that if a theorist like me, may be interested to be involved, then I see a room to enter into.
It's a great question, and I think I'm going to rephrase it like that. Like, how much is this approximation holding? Like, how true is it that we can describe the polarizability of nanoparticles as a dipole? Like, within which actual range of frequencies or nanoparticle sizes does that actually count? Of course, this is exactly the Rayleigh condition. So if you take a nanoparticle, a microscopic nanoparticle, let's say a micron size, and you want to know how it interacts with the electromagnetic wave, you have to go through virtue and suffering, and that is the called me theory. So these are me resonances in spherical objects. As you make it smaller and smaller, those me solutions, they collapse into the Rayleigh scattering, right? If you go to the molecule, the reason why the sky is blue is because it scatters a lot of the blue light. And the two are actually seamlessly merging one into another. Now, up to which dimension this approximation holds depends very much on the material. So, and in particular, I can give you an example. For gold, this approximation is pretty okay until a few tenths of nanometers. So maybe 20, 30, 40 nanometer particles. The resonance frequency is at least the same. Now, the line width will not be, because as you make a nanoparticle bigger, you also make your plasma resonance wider, because you start to get the retardation effects because of the dimensions of the nanoparticle. For silver, it even breaks down even sooner. I think already at 20 nanometer, this approximation doesn't hold anymore, because silver is actually has this permittivity that is very steep in wavelength. And so the plasma resonance actually shifts a lot as soon as you make it a little bit bigger. The other thing, complicating factor, is that this is only the dipolar solution in Mie theory. And it's actually only the electric dipole in Mie theory. Mie theory has electric and magnetic dipoles. There is also magnetic fields, which I never talked about, and also has electric quadrupole and hexapole and octupole and so forth. And so, for example, if you take a silver nanoparticle, you make it 60 nanometer in solution, you will see a strong peak at 420, but you also actually will see an emerging peak at around in the UV, and that is the electric quadrupole that is starting to show up. And if you make it even bigger, then you get hexapoles. And so the picture becomes much more complex. Yeah. And these can have all sorts of effects, not only in nanomaterial synthesis, like I discussed today, but in photocatalysis, but also in like nano optics, light steering, surface enhanced Raman scattering, like any application of nanophotonics and metal nanoparticles will be influenced by these aspects. And to be honest, for everything that we do in our labs, we never use this approximation. We have written our own MATLAB script, and we can solve we can solve for Mie theory. So we always calculate the actual absorption and scattering cross-section for spherical objects. In fact, for most of the stuff that we do in our lab, we don't even use Mie theory, because that's only for a spherical object or for an prolate or oblate spheroid. But most of the stuff that we make is actually more complex than that. And so in order to solve for Maxwell's equations, we use finite difference time domain numerical solvers. Yeah. Let's say Mie theory is the lowest level that we go. Yeah. But it's actually relatively simple. So my students and I, we went through the virtue and the suffering. And so we have written our own MATLAB code. I've actually uploaded it on GitHub. I don't know if you're using MATLAB, but if you want to calculate the scattering and absorption cross-section of any spherical object in using the full Mie theory, there is a MATLAB code that is freely available on GitHub. Yeah. Yeah. So the question, maybe, I don't know if the people online heard, is there any way that we can use DFT? And yeah, that's a great question. It's extremely relevant for photocatalysis, right? So to describe the nanophotonic properties of these metal nanoparticles, macroscopic metal nanoparticles, DFT fails. We're talking about tens of nanometers. DFT cannot handle that. There is way too many atoms. A 10 nanometer particle, 30 nanometer particle has something like 3 billion atoms. Something like that. A 10 nanometer particle has 30,000 atoms, something like that. So that's already, and each atom has a lot of electrons, because these are kind of transition metal elements. However, it is extremely relevant for photocatalysis, and there is a lot of papers in photocatalysis that include DFT calculations, because the energy levels at the surface are crucial. So understanding the molecular orbitals and how they're changed by the interaction with the electronic levels, the electronic density of the metal, is crucial to understand catalytic reactions. In fact, catalysis, the reason why a metallic surface activates catalysis is simply because you have a molecular orbital of a molecule, and when it gets close to a metal surface, those molecular orbitals are changed in energy and broaden. And there is a finite probability that some electronic density will populate an anti-bonding orbital of the molecule. And that's how you weaken the bonds. So having a DFT calculation of an interface between you can make a Jellium approximation of your metal and some molecular orbitals. It's something that is very useful and very often done in plasmonic photocatalysis.
If I may add, I think we had this discussion before with Pak Aziz. I think what can he contribute to the field? And I said that, yeah, in this plasmonic fields now is the one that's quite hot is this plasmon-mediated catalysis, right? And there are groups that use this DFT, time dependence DFT, that basically, like Andrea said, usually calculating the orbitals of the surface and then the molecules that they want to transfer and so on and so forth. I think Paul Erhardt is working a lot on that one. We both work with Paul Erhardt, and I know one of our former postdocs now in Finland, my ex-college, are working on that one. Maybe I can later share with you, Pajis, all of this paper. Then maybe we can have some discussion on it. So indeed, DFT with this, since now, like Andrea said, plasmonic is no longer like a physics problem, but now it's more on chemistry. So I think a lot of orbitals, a lot of coordinations, and yeah, this chemical reaction, I think that's from density of states and so on. So DFT is really powerful for this one, at least now.
I think if someone can come up with a creative way in which to calculate potential energy landscapes of reactivities of a metal molecule interface with a cheap, computationally cheap method, that would be fantastic, right? Because it's extremely difficult to do. There are way too many electrons and metal and atoms to take into account.
So I think it's time for Pazis to recruit some students and make it happen. I think we have a question from the audience online. So we have 2 questions. So maybe one first, and we go through the audience here again. So thanks for your nice presentations. The question is how the mechanism of surface plasmon resonance on metal oxide decorated with noble metals, for example, zinc oxide silver, zinc oxide gold, enhance photocatalytic degradation for dye. So basically, how this composite system of metal nanoparticles and oxides can enhance photocatalytic performance, for example, in the degradation of dyes.
Okay, yeah, I think they're mentioning like a metal oxide particle decorated with metals. Is that the case?
Yes.
So
maybe the other way around. So can happen the other way around.
Yeah, so this goes back to the previous question that so far I only discussed the resonances of metal nanoparticles. But as I said, these are me resonances, right? Any spherical object of any material can sustain one of these resonances. If you have a metal oxide, of course, you don't have free electrons, but you can have polarization. And this dielectric nanoparticle, they can sustain, for example, magnetic dipoles. So this would be polarization currents that are orienting one side in one cycle and the other side in the other cycle, essentially pointing a magnetic field up or down. That's a magnetic dipole. And so they can also strongly interact with light. So if you have a metal oxide nanoparticle decorated with the metallic nanoparticles, you would have to solve Maxwell's equations. Probably you would have to do a finite difference time domain or like a frequency domain numerical solution. And you will find that there is probably going to be field enhancement on the surface and, driving of polarization on the surface. Probably there is, hot electron generation in the metals. I wouldn't be surprised. Yeah. But this is a very hierarchical system. So you cannot just use a simple spherical approximation for a very small particle of a perfect conductor in vacuum. Like all of these conditions are breaking down when you have such a hierarchical system. So you really have to do the hard work of doing the full calculation.
Okay, I hope that answered the question. Is there any question from this room? Prof. Terry, maybe? No, pass? Okay, please.
Hello. First of all, I want to say that the presentation was very insightful. Okay, my question is actually very basic and related to chemistry. I want to ask that why there is a need to explore the activation of reaction with nanoparticles, although we have catalyst available and widely used. I just want to ask that using nanoparticles are more effective than the catalyst. Thank you.
Yeah, great question. And that's a question that I fear every time that I write a proposal, like, why are you doing this, right? There are a couple of reasons. One is that controlling the charge state and the heat at the surface of a metal nanoparticle is a great tool if you know exactly how to do it, to modify the surface chemistry of the nanoparticle and actually learn something about the process. So if we want to learn something about, for example, the activation energy of a specific catalytic reaction, using light to control the temperature locally or the surface charge locally can be a great tool, analytical tool to study our system. So one aspect is fundamental studies of what the hell is happening. Light is a great tool both to incouple, to control, but also to outcouple, to study whatever is being formed on the surface, for example. The other thing is that light seems to be doing something very different from whatever is happening in the dark. So there was a seminal paper by the group of Sulio lineage in 2011. I think this was a Nature Chemistry or something. And what they did is they studied a reaction that is the epoxidation of propylene. So propylene is a hydrocarbon with 3 carbon atoms, and 2 of them have a double bond. And you want to form an epoxide. So the double bond, essentially, you add an oxygen that bridges the first 2 carbon atoms. The reason why this reaction is very difficult is because you have to oxidize a hydrocarbon. Now, oxidizing a hydrocarbon means burning, essentially. So if you oxidize it a little too much, you form CO2 and water, and you get a flame out of it, right? So you want to oxidize it, but just a little bit. And so they run the reaction typically using copper nanoparticles, which is a good catalyst. And then if you run it in the dark, 20% of your propylene becomes propylene epoxide, which is what you want, and is a great molecule to start, for example, a variety of industrial chemical synthesis. Now, what they discover is that, okay, if we run this reaction in the dark, we get 20% of the product that we want. But then if we run it under light, so the same catalyst, the same setup, now they added a window and they started shining light onto it, and then they get 40% of propylene epoxide. And the question, okay, how did they go from 20% to 40%? Their idea, their explanation back then was that if you shine light, you're generating these electron hole pairs, and the electrons are actually able to reduce the copper oxide that is formed at the surface. Copper is a very sensitive metal. It gets oxidized very easily. So you always have a native oxide on the surface. And of course, if you have an oxide on the surface, the catalytic properties change dramatically. But if you can somehow refresh the surface by shining light onto it, apparently you double the amount of the product that you want. So these kind of seminal studies really open the way to, okay, let's see if we can do something not only more, but also better with light. And that seems to be possible. So light is a very funny chemical ingredient. It behaves in funny ways. And that's why it's important to understand exactly what's going on at the fundamental level.
Thank you so much. I got my answer. Thank you.
Thank you.
Or question online. Maybe you can read it yourself because it's too long.
Which one?
Dedi Riana, for the study of surface plasmon polaritons. So I will read it for the audience. For the study of surface plasmon polaritons in planar structures, such as in prism-based SPR sensors, an addition layer is usually added between the substrate and the plasmonic film. Is there a difference between having and without an addition layer? What phenomena might account for these differences? I think this is also a debate that I always have with Andrea, because Andrea always had addition layer, but I never in my 13 years of career use one. So yeah, but the question is yours.
Yeah, I think this is a very technical question. Actually, it's so the question is, very often people take a glass substrate and then they grow a gold film on top of it. And then the gold film will be very flat at the interface because the glass is extremely flat, but on top it's rough because it doesn't grow perfectly. And so this roughness is able to launch not localized surface plasmon, but actually propagating surface plasmon. These are density, essentially are charge waves at the interface between the metal and the substrate. And so these are different plasmons. They're called surface plasmon polaritons. They travel, they can be used for sensing, they can be used for many different applications. And the question is, okay, when you grow gold on top of glass, typically gold doesn't stick too well to glass because gold is a noble metal. And the way metals stick to glass is by oxidizing a little bit. That's why if you deposit aluminum on a metal, you get a fantastic addition, or chromium just doesn't react on the surface, on the interface, and so it doesn't stick too well. And so what people typically do is they add a chromium layer or an aluminum layer, and then on top of it, they put the gold. Now, of course, a gold film will have optical properties that are different from a chromium layer with gold on top. So the optical properties do change slightly. I think, for SPR, this probably does have a huge effect for localized surface plasmon resonances, particularly if we're making nanostructure with nanolithography. We are always interrogating them from the top, so we are not very sensitive to whatever is happening on the bottom. And as Ferry was saying, like you don't even need that addition layer. So if you can get rid of it, it's probably best. Because these metals that are used to increase the addition are typically very good at addition properties because they get oxidized, but also they're very bad plasmonically because they have large losses. So you stick your nanoparticle to the substrate, but you lose in plasmonic quality. So if you can get rid of it, get rid of it.
Yeah, thanks. Is there a question from the audience here and from the online? No? Maybe last chance, yep.
Maybe the possibility of students requesting to be supervised by
As an external supervisor. So the student would do the thesis here, and maybe there can be a collaboration, like yeah. Yeah. So I think, as I mentioned at the beginning, I'm super willing to accept like rotating students, like master students or PhD students that can, fund, come with some funding to sustain themselves. Open arms, by all means. I don't know about master students, whether they can come and do a thesis in our laboratory. This is something that I would need to check with my university. But if the answer, I would say the answer is 99% yes. And if the answer were left to me, the answer is 100% yes. So open doors, and hopefully if there is one output of this trip is that, there is stronger collaboration between the institutions in here in Jakarta, like Photonics Center yesterday and the University of Indonesia and the Vrije Universiteit. Yeah.
Yeah, I think if I can clarify what Mr. Aziz wanted was, if it's possible for you, maybe you have a little bit more free time, then you also supervise students basically studying here. So then the supervision will be done like probably online, maybe every 2 weeks or every 1 month. Yeah. Yeah. So basically collaborations,
Yeah.
but then since probably we don't have all the expertise, I think it's nice if you can also like act as a supervisor. So if there is any problem, we can ask you and you have some
Yeah.
time to explain and to direct maybe the research. I think that's what Mr. Aziz is asking,
Yeah.
right?
Yeah, absolutely. I mean, if it's a project that is relevant to what we do and it overlaps with what we do, I'd be happy to. Like, I've done it this last spring with a PhD student from the group of Paul Erath,
Okay.
and she even came to the group for 4 weeks. And even now, she's still using our software tools from remotely from Sweden. Now she's back in Sweden, and we're collaborating still on the project. So yeah, for sure. If we can, if I see research overlap and I see that I could contribute, I mean, if it's about DFT, I'll take a step back because I know nothing about. But yes, for sure. Yeah.
Is there any more questions? Mas Gary, ada? No? So otherwise, I think we should close the session. I think it's really nice talk and really good discussions. I think it was really wonderful. So thank you very much for coming. So again, tomorrow Andrea will also present in dekanat, ya, multidisiplin. If you enjoy his presentation, he already made impression on me. Like, this guy is really good at presentation. And it hasn't changed even until now. It's not better probably. So yeah, please do. I mean, we will learn because this is also soft skills. I think Mr. Aziz that said, yeah, I think this is really good skills for you to have not for only scientific, but also for your career, whatever you might be. So, and this is also really good. So please do come if you are interested. And as a lecturer myself, I will actually ask you to go there if I have if I have the power. But I'm afraid I don't. But yeah, that's it. So thank you very much. So we'll see you again probably, hopefully, sometime soon, or maybe next year, or we don't know. We might do it yearly probably. Okay. Oh yes, and also we have, as usual in Indonesia, it's a certificate, so you should learn by now. As a token of appreciation, and we are really grateful that you are here sharing the knowledge with us. So maybe Prof. Terry will come here and give the certificate.
So I think you should stand here because this is tradition. And is it okay? You want to make a photograph? Okay. So, well, I should say something. So Dr. Andrea Baldi, in recognition of valuable contribution as speaker in the seminar on plasmonic chemistry, activating chemical reactions with metal nanoparticles, Department of Physics would like to extend this certificate to you for thank you. Thanks. So we have to make a photo. So thank you very much. Thank you very much. I agree. Wow.
Such as emergent properties, I try to count physics. Okay.
Thank you so much.
Kita foto-foto ini?
Foto nih, saya mau ngajar.
So let's have a quick photo session. If there's no photo, this thing never happened.